Title of this webinar is The Art of Failure Analysis of Printed Circuit Boards and Electronic Components, Root Cause versus Red Herrings. And again, I'm Joe Bedard. So let's get started. So first, I'd just like to go through an overview of what we're going to be talking about today. The first thing we're going to talk about is PCB, or Printed Circuit Board, FA Considerations. And then I'm going to go over 4 case studies, as well as some phenomena or anomalies that are observed in PCBs themselves and plated through holes. So for the first case study is going to be PCB module number 1. We're going to look at a PTH assessment. In this particular case, we're going to look at both vertical polished samples in the as polished condition and in the as etched condition, and we're going to talk a little bit about that. The next thing we're going to do is we're going to talk about PCB and PTH phenomena and anomalies, and we're going to go over select anomalies that are observed in both PCBs and PTHs. The next thing we're going to do is we're going to do PCB module number 2. That's going to be case study number 2. That's going to be a VIA assessment. And here we're going to look at a vertical cross-section in the as-polished condition, in the as-etched condition, horizontal cross-sections in the as-polished and as-etched condition. We're going to go over grinding and polishing techniques that are not recommended. So we're going to look at both sections that I prepared in a recommended manner, and then we're going to show that we may potentially hide or obscure anomalies or defects in poorly prepared cross-sections. And then lastly, for that second case study, we're going to review aggressive etching techniques, and we're going to do a comparison of proper etching, sample etching versus non-standard sample etching. Then we're going to go over a multi-layer ceramic chip capacitor, FA. In this particular case study, we're going to concentrate again on proper cross-section sample preparation versus non-standard sample preparation techniques. And then the last thing we're going to talk about is a complex integrated circuit FA. In this particular case study, we're going to examine de-encapsulation processing and how that may or may not affect what's viewed in the actual integrated circuit after the package has been de-encapsulated. So let's get started. So PCB FA considerations. Any failure analysis should start with a good history of the failed samples, and this should include what the failure symptom or symptoms are, whether it's an open circuit or short circuit, etc. This particular information is critical to the analysis. We want to be able to target the analysis to attempt to target that failure symptom. We want to let the data speak for itself, obviously, but the failure symptom understanding is quite important here. The next thing is we want to understand the sample history. We want to understand, was this infant mortality? Was it a burn-in failure? Has it been in the field? How long has it been in the field? Was it one particular geographical location in the world that we're seeing this failure, etc.? What the approximate failure rate is? All these things are important to know before starting any failure analysis. The next thing we want to do is we want to make sure that we have at least one control sample, so one known good or new sample that's the same as the samples we're going to be analyzing for the failure. And we need to treat this control sample in the same fashion that we treat the failed samples. That is to say, any sample preparation, cross-sectioning, analysis, etc. needs to be done similarly on the control sample as it is on the failed samples. As far as PCB failure analysis goes, we want to make sure that we use proper coupon extraction techniques when we're actually removing a certain section of the board that we're going to end up cross-sectioning subsequently. And we'll talk a little bit more about this later. And then we want to make sure that we're using proper cross-section sample techniques. And I'll go over this, and I'll actually demonstrate what happens when we don't use proper cross-section sample preparation techniques versus when we do. So that's an overview of the presentation. So case study number 1, PTH assessment. So here we have a optical image of a printed circuit board module. In this particular case, it looks like it's a display. Over on the left-hand side, we have an area outlined in red. This is going to be the component that I'm targeting for the plated through-hole analysis. And we're going to go to the next slide. So here again, we have side 1 of this particular module showing the region of interest here outlined in red. And over here we have side 2 of this particular module, and again the region of interest is indicated in red. Here we have some higher magnification images of that particular component, and we can actually see we're going to do a vertical cross-section here. We're going to cross-section through this row of PTHs, and the vertical plane or the viewing plane is going to be in this direction where these arrows are pointing up here. Again, over here on the right-hand side we have side 2 of the module, again showing this cross-section plane here and showing the viewing angle or viewing surface here. So again, they're going to be vertical cross-sections in this particular sample. Here on the left-hand side we have an extended depth of field oblique view of just of the component of interest. And again, on the right-hand side, we actually have the coupon after I've extracted it from the PCB. So this is quite important. We want to make sure that we're at least several millimeters away from the region of interest here. If we were too close to the region of interest, we may induce defects that are not intrinsic to the PCB module. And we want to make sure that we use extraction techniques that are recommended. I've seen cases where people may use a punch and die setup, which would not be recommended. In this particular case, I've used a Dremel tool to carefully remove and cut out this coupon. And again, paying particular attention to make sure that I was several millimeters away from the region of interest here. So here we have a couple of vertical cross sections. On the left-hand side we have a PTH with the component lead coming down through the PTH. We have some solder which has filled the PTH here. A couple of things to point out. Again, we have the component lead. We have an outer layer knee region that I've indicated because I'm going to be talking about outer layer knee regions further in the webinar here. Again, we have the PTH. We have the plated sidewall of the plated through hole here, the laminate material here, etc. On the right hand side, this is a higher magnification image of the side 1 outer layer knee region in the as polished condition. So here we haven't applied any wet chemical etching at this point. It's always recommended that the sample be looked in the as polished condition prior to any etching. If there were any cracking, etc. at this outer layer knee region, that may be revealed in this as polished condition. So here we have some higher magnification images of the plated through hole sidewall. This is about in the center of the sidewall. We have again the solder, the plated copper, and then the laminate material of the PCB. This is a good quality, prepared cross section here. Again, layer 2 or side 2 knee region here. Again, the plated copper, etc. Again, this is in the as polished condition. This analysis is just to demonstrate what a properly polished sample looks like at this point. So here we went ahead and etched the sample with a wet chemical etch using a method that would be recommended, proper etchant. And again, we'll talk about aggressive etching, etc. later in the presentation. So again, we have the component lead, the plated through hole sidewalls, etc., solder. Here's a higher magnification image similar to the one we saw earlier, but this is in the as-etched condition, and we'll talk a little bit more about this in the various layers that we can see here in the next slide. So here in the next slide we can see the sample in the as-polished condition, and we can see the same region in the as-etched condition. And here in the as-etched condition, we can see certainly the component lead has its own grain structure. The plated copper has a grain structure here. Here we have what's called an electrolysis copper layer that's added on prior to the electroplated copper here. And here we have an outer layer foil region. So it's important that we can see the grain structure in this outer layer foil region. We can see the electroless copper here, and it's not over etched or very black or dark or voided, etc. And we can see the grain structure in the outer layer plated copper region here. Those are all very important. Again, similar to the previous images I showed in the as polished condition, this is a region probably near the center of the PCB, PTH. We have the solder that's filled the hole, the plated copper, and then the laminate material in the board itself. And again, similarly, the side 2 knee region here, we can see that this is in the as-etched condition, and that we can see the difference between the grain structure here and the plated copper. We can see the electroless copper, which actually extends down through the entire length of the plated through hole here. The electroless copper is added prior to the electroplated copper in order to make make this laminate material electrically conductive so that we can add the electroplated copper. And again, we have the outer layer foil region here. So the next thing I want to talk about is PCB and PTH cross-section phenomena. Now this is a cartoon graphical that I pulled off of a IPC website. I've got them listed down here, and you can see there is a myriad of different phenomena or anomalies that may occur both in PTHs and in the PCB in general. The next couple of slides I'm going to go over a couple of select items here. There's just not enough time for me to go over everything on this slide for this presentation. But you can see that certainly there are a lot of things that can go wrong with a plated through hole and in the PCB in general. And there's actually more things that are listed here as well. So this is just an excerpt from that previous slide. We have 4 different items here, 4 different phenomena that I'm going to talk about. Number 7 right here is a bond enhancement removed. So on the smooth side of the inner layer foil here, they've added a black oxide preparation step to create a greater surface area and bonding strength to the inner layer laminate material here. So in this particular case, it's missing, and if we were to look at this in the horizontal orientation, this would be called pink ring. And basically, this would be a black region here, this would be pink, and again, it would be another common name for this is pink ring. The next phenomenon we're going to talk about is a hole plating void, which is number 10 here. So this is an area here where it looks like there's electroless copper that was applied to this particular plated through hole, but for one reason or another, maybe there was some debris, maybe there was an air bubble in the plating solution, etc. There was a void that had happened in this particular location. So it's a typical hole plating void. The next thing we're going to talk about is number 11 here. This is a wedge void. So in this particular case, there probably was a small gap or void present at the inner layer foil to laminate resin region here, and when they did the electroless copper overplate, it didn't actually plate in this region. So then when they did the subsequent electroplated copper, we see this wedge void, which is at the region where the smooth surface of the foil reaches the or interfaces with the resin material here. And lastly, in this particular slide is a glass fiber void. So again here, one or two of these fibers probably protruded out when the hole was drilled. They may have been rough. Electroless copper was not able to plate that region because of the roughness, etc. And thus you get this glass fiber void. So on to the next slide. So again, here we have 5 different phenomena or anomalies, and again, these selected anomalies I just pulled out of that larger slide. A couple of these we're actually going to see later in the presentation and samples that I've actually prepared myself. The first one here, number 20, the knee burr that's pushed into the hole. We can see this region here. So this was probably due to poor drilling techniques that were used. Either feeds and speeds were wrong in the hole drilling, or there were too many hits on the particular drill, and we got this particular burr that occurred because of that, and it's actually protruding out into the plating here, into the hole. And we're going to see a little bit about that. We're going to see one of those a little bit later. The next thing we're going to talk about is number 21 here, the glass fiber protrusion, and we're going to see this as well in one of the sections that I prepared, is where the glass fibers are actually punching through into the copper plating here of the hole. Number 32 here is a copper foil contamination. So that's up here. Basically, there was some contamination left on the copper foil before the electroless copper, and then the subsequent copper plating was performed, and that foil contamination got trapped inside of the outer copper plating here. The next thing we're going to talk about is this lifted land, number 33. So this often happens after the sample has gone through SMT or solder mount technology processing, where there's been some thermal activity placed on the board. It's gone through a wave solder, etc. And oftentimes what will happen is you'll get these outer layer knee regions or outer layer lifted lands, and you'll also get subsequent either cracking or delamination or even voids in the resin-rich epoxy material here. And then the last thing we're going to talk about, the last phenomenon here we're going to talk about, is this resin crack delamination. That's number 34, and that's right here. And that's just a crack or delamination that's occurred in the resin-rich region of the PCB laminate material. So case study number 2, a VIA assessment. So here we have an optical image of a fairly sophisticated printed circuit board module, and we're actually going to extract a couple of coupons from this module. We can see them, I've indicated they're here in red. One of these coupons is going to be used for a vertical cross-section analysis, and the second one's going to be used for horizontal cross-section analysis. So here we have that same module. This is side 1 of the module. Again, we have the 2 regions that we're going to be targeting here. And here's side 2 of the module. We can see that there's only, the side 1 is the only side that's populated. Side 2 is not populated. So there's various components, connectors, etc. on side 1, where there's none of that on side 2. And again, these are the 2 regions that we're going to indicate. One of them, again, I'm going to be using for vertical cross-section analysis, and then the other one for a horizontal cross-section analysis, or plan view cross-section analysis. So again, here's a coupon that I had extracted from that particular module, and this is the coupon we're going to be using for the vertical cross-section examination. And we can see, again, we want to make sure that we're a good distance away from the regions of interest. So the regions of interest are going to be these vias right here. We can see the cross-section orientation and approximate location here, and we can see that the plane of view is pointing up here, so this is going to be a vertical cross-section through these vias. And again, I just want to reiterate that we are a safe distance away from those vias, so we don't want to incur any damage to the vias by cutting too close to them. Any damage or any anomalies that may not be intrinsic to the device itself or the board. Okay, so here we have an overall view of a via in cross-section. If you remember the first PTH that we looked at, the sidewalls on the PTH were relatively smoother than this particular via, and we'll talk about these locations where we see this roughness of the plating that's been added going forward here. On the right-hand side, we can see an outer layer knee region, and we can see we haven't, this is in the as polished condition, we can see we have this anomaly here that I've indicated with these red arrows, and we're going to see some more about that again going forward. So again, looking at this in the as polished condition, we want to understand what the sample looks like in the as-polished condition, so that when we see things in the as-etched condition, we want to understand that they're anomalies or phenomena that weren't added by the etching condition but that were there previously. Sometimes etching, and more often than not, etching will enhance a crack if we see it in the as-polished condition, or anomaly if we see it in the as-polished condition, but it shouldn't add any cracking or phenomena. So here's a higher magnification of what I was alluding to a little bit earlier on the previous slide, where we had this roughness coming down through the via, and we can see here that this particular resin-rich region of the laminate material, when they did their etch back of this hole, the resin-rich area was aggressively etched back, more so than the first PTH, or the case study number 1 that I talked about. Now here, there's no particular harm or foul, there's no real defect, but potentially this could be a region where we would develop maybe a plating crack or a plating void. And going back to the couple of previous slides when I was talking about the phenomena that were observed in various PCBs, one of them was glass fibers protruding into the plating, and we can see that here a little bit. We can see these glass fibers that are protruding into the plated region. This is a bright field image of this defect. This is a dark field illuminated image of this defect. And again, I've got the region circled in red. Here's a resin-rich region here. These are glass fibers that we're looking at these longitudinally, and these are glass fibers that we're looking at in the transverse orientation. And again, this resin-rich region was etched back slightly more than the fibers were when they did their etch back after they drilled the hole, or after the hole was drilled. Here's just a layer 2 or side 2 knee region, again in the as-polished condition. And again, this is using proper sample cross-section preparation techniques. We're going to go over both proper, we're going to look at both proper sample preparation techniques versus ones that I would not recommend, as well as aggressive etching as well, a little bit later here. So here's that via in the as-etched condition, and here's that same region that we looked at before in the as-polished condition. We saw this defect in the as-polished condition is now in the as-etched condition. And we can see I've got that indicated here, and we can see a higher magnification image here. So a couple of things of note here. We can see that they've used 2 plating strikes for this particular via, or this particular device when it was built. We can see there's a thinner plating strike here. Here's the interface, and then a thicker plating strike here. We can also see this debris, which is most likely left behind after they drilled the hole, they did their etch back. This is just debris that was left behind. We can also see a defect that I alluded to earlier in the phenomena slide, where this little burr is not quite extending too far into the hole, but there's a small burr here. And again, this is probably caused during the drilling procedure. It's just an extension of this very small burr right here. Again, here's that slightly over-etched resin-rich region here in the as-etched condition of this copper plating. So here's an outer layer knee region, side 2 of this particular via, where we see a very subtle anomaly here at the electroless copper layer. Here's a higher magnification of that. I've got it circled in red. This is a very subtle anomaly observed. These could be voids at this electroless copper layer here. If this particular defect or anomaly was located on an inner layer interconnect region and was around the whole circumference of the plated through hole, this could be a catastrophic defect where there would be an open circuit or high resistance region at that particular layer causing potentially overheating condition or an open condition if it was totally open circuit. In this particular case here, this is the worst observed anomaly, where we have this buildup of material that was left behind after the drilling procedure. It wasn't cleaned properly. Again, this could lead to some type of a plating crack or plating void, etc., but we don't see those particular phenomenon in this instance. Again, this is a higher magnification view of that anomaly. This particular anomaly was not indicated in the previous slide that I showed, with all the various phenomena that may occur in plated through holes and PCBs in general. So now we're going to talk about horizontal or plan view cross-sectioning. So here's a region that I removed the coupon for plan view assessment of this particular PCB. And here's one of the vias in cross-section, and we can actually see those anomalies that we observed earlier in the vertical orientation are located in these regions I've circled in red. Now, if we had cross-section this particular via in the vertical orientation through this plane here that I'm showing you with my mouse here, we may not have seen these defects. So that's why it's often important to look in the horizontal orientation as well, to understand how far around the via or PTH that these defects are extending. Again, here's a higher magnification of one of those anomalies that we observed earlier in the as-polished condition. Similarly, another high magnification view of one of those anomalies in the as-polished condition. Here we have a second via that I've cross-sectioned in the horizontal orientation, and we can see that anomaly actually extends almost 50% of the circumference of the via in this particular case. And again, just a higher magnification view of the anomaly in the as-polished condition here. Again, a higher magnification view of a select region of the anomaly in the horizontal orientation. Here we have a similar view of the via that I showed earlier. This is in the as-etched condition, and we can see that the anomalies look a little more pronounced in this particular case. Again, the etching tends to obviously reveal the grain structure, but also reveal those anomalies in a more distinct manner. Similarly, here we have those anomalies in the as-etched condition. Again, one more image in the as-etched condition. So here we have a composite image. On the left-hand side here, we have the defect as viewed in the vertical orientation, and on the right, we have the defect as viewed in the horizontal orientation. So again, oftentimes it's advantageous to do both vertical and horizontal cross-sectioning activities to view these various defects and understand, in this particular case, how far around the circumference of the plated through hole that particular anomaly extends. Excuse me. Okay, so let's talk about intentional poor sample preparation. So I've traveled to various PCB manufacturing vendors nationwide where these particular vendors were submitting boards for a qualification effort. I went ahead and cross-sectioned them. They had indicated that they had met the specific specification that they were manufactured to. I went ahead and cross-sectioned them and found that there was one or more anomalies or defects that were present that the board manufacturer didn't locate or notice when they did their cross-sectioning activities. So I traveled out to their facility and viewed their laboratory personnel, and viewed their cross-sectioning sample techniques and practices. And oftentimes what I found is that they were taking shortcuts. They were either using too much pressure when they were performing their grinding and polishing techniques, which will often yield a cross-section that looks fairly this section's nice and flat, relatively free of scratches. It looks pretty good, but if you're cross-sectioning feeds and speeds, wheel speeds are too fast, the pressure that you're putting on the sample when you're doing the cross-section sample preparation is too great. You're going to smear some of this copper over, and you're going to maybe obscure some potential anomalies that may be catastrophic. So again, this is a case where, geez, this looks pretty good, you know, in the as-polished condition, but we may have some smearing going on in this region here. This on the right-hand side is an as-etched version of the intentional pour sample preparation that I did on this particular sample. And if you remember back, we saw a couple of anomalies here at this electroless copper interface that we're not seeing here in this particular sample. Here we have the sample that was prepared properly using proper cross-section sample preparation techniques on the left-hand side, and we can see those anomalies that are fairly subtle here, but they could be you know, catastrophic in nature if they were any larger. And here we see the sample that was prepared using intentional pour sample preparation techniques. And again, what I did is I used wheel speeds that were not recommended. They were too fast, and pressure on the sample that was too great. So probably got some smearing of this particular foil over into the plated copper. We can still see a demarcation of the electroless copper, but those defects may be hidden by this smearing, the smearing of the copper in this particular case. So it's critical that that proper cross-section sample preparation techniques be followed. And this is a type of defect that I would find while doing the assessment at the laboratory that I was working at, and then traveling out to the PCB manufacturer. We would actually prepare the same samples that I prepared using their methodology, and I would then prepare them on their equipment using my methodology, and we would examine them side by side. And in almost every case, we would see that these particular defects or anomalies would show up in the samples that we had prepared using the methodology that I recommended, and they would either be masked or hidden by using the methodology that they were previously using. So let's talk about some over-aggressive etch chemistry. Again, traveling out to these printed circuit board manufacturing facilities, I found that oftentimes they would be using etch chemistries that were quite aggressive, and they would only make them at the beginning of one shift, and the particular etch chemistry would be used throughout the entire shift. So at the beginning of the shift, it would be very aggressive in nature, and at the end of the shift, the etching chemistry would be spent, and it would not be etching the sample enough. In this particular case, this was a freshly made batch of this over-aggressive etching solution. And we can see here at this electroless copper interface that it's a very dark line, and it actually looks like a separation. This would be misconstrued as, you know, a separation. If this was in an interlayer region, it would be misconstrued as a potential electrically open region. We can also see that using this aggressive etch, that the amount of etching varies greatly within a small area. We can see this over etching here, and then we can see it tapers off to almost nothing, where we can't even see the electroless copper layer out here in this region of the knee here. So it's just not a uniform etch that you get from this aggressive etching. We get, you know, an area here that we would call this an anomaly. This would be it looks like a separation to me of this particular region, when in fact it was caused by the aggressive etchant used. Here we have another composite image showing the properly prepared and etched sample here versus the aggressive etch sample here. And again, these particular defects are masked by this black line here. And again, we would think that this was either an anomaly, or in one of the cases when I traveled to a PCB vendor, they indicated that this is what they look like all the time, so we think that this is normal, when in fact they had anomalies such as these present and weren't able to see them. So it's critical that the proper cross-sectioning sample preparation techniques are used and that proper etching techniques are used to reveal these defects. So the next thing I'm going to talk about is a multi-layer ceramic chip capacitor failure analysis. In this particular case, I'm going to be discussing proper cross-section sample preparation techniques of these MLCCs. Oftentimes when we look at MLCCs that have failed, either open, high resistance, etc., we often do serial cross-section sample preparation of the MLCCs, and typically we'll take 3 slices through the MLCC, about a quarter of the way through, a half of the way through, and then 3/4 of the way through. Here I've just prepared one cross-section through the center of each of these MLCCs. Again, this is the cross-section plane, and then the orientation is facing in the up direction here, so we're looking at the MLCC in the vertical orientation, including both of the solder joints or the attachments to the PCB module. And we're going to do this for 2 different MLCCs, and I'm going to show you what a properly prepared cross-section of an MLCC looks like versus one that I've intentionally poorly prepared. So here we have the MLCC in cross-section. This was the technique used here was proper cross-section sample preparation. While doing this, I did see a couple of anomalies in the PCB that we'll talk about a little bit later. But here, let's focus on the way that the MLCC looks. That there's no chip outs. It's nice and smooth, free of scratches, etc. This is just a higher magnification view, partial view of the MLCC. We can see, again, no chip outs at the interface here between the MLCC and my mounting epoxy. Nice, flat, and smooth. The black dots that we see in this image are intrinsic to this particular MLCC, and not from the polishing process. Here we have the MLCC that I prepared using preparation techniques that would not be recommended, mainly jumping from a coarse grit silicon carbide grinding paper to a very fine grit in one fell swoop. And we can see we have these chip outs at the interface between the capacitor itself and my mounting epoxy, both on the top and less so on the bottom, but certainly there as well. And we can also see this demarcation here, which is a scratch probably from a previous grinding step, coarse grinding step, that did not get taken care of during the fine grinding step. So this would occur if you're jumping from a very coarse grinding paper to a very smooth grinding paper without using any intermediate grinding papers in between. Here we have a high magnification view of the MLCC with some chip outs observed here. Again, these were caused by the improper cross-section sample preparation techniques. Again, this is the MLCC material. We have the dielectric, and then we have the electrode material here, which is brighter in color. And we have these chip outs, and we have my mounting epoxy here. A little bit more about that defect that I observed. It's a delamination or a void here between a glass fiber rich region and a resin rich region near the surface of the PCB. It's actually caused this land or this pad that the MLCC was attached to buckle. This most likely occurred during the SMT processing when some thermal activity occurred during that processing. Again, here's a dark field illuminated view of this particular delamination between the glass fiber filled region and the resin rich region here, and potentially a crack right here. And again, this caused buckling of the pad, the land that that was associated with that MLCC. Here we have a composite image showing the properly prepared MLCC cross-section on the left-hand side, this guy here, and the MLCC that was subjected to non-standard or improper cross-section sample preparation techniques here. And we can see the defects associated here with that sample preparation techniques, these chip outs, this particular scratch here, etc. Again, just higher magnification views of the MLCC and the properly prepared or recommended cross-section sample preparation techniques here, and purposely poor sample preparation techniques here. Again, these chip outs are associated with the poor sample preparation techniques. So again, you can see it's critical that proper sample preparation techniques be used so that defects that are observed that may not be intrinsic to the device may be observed. So in the case where we're doing poor cross-section sample preparation techniques where they were used. So lastly, I'm going to talk about case study number 4 here. This is a complex integrated circuit, and we're going to talk a little bit about actually removing this outer layer package material to get to the integrated circuit itself. That's typically a wet chemistry methodology that's used, and that's what was used in this particular case. So this is just an optical image of the complex IC that I'm going to perform a de-encapsulation of in this particular case. So again, here we have an optical image of the integrated circuit, basically as received, and it's always recommended that we optically document any sample before doing any failure analysis. So we want to do a proper non-destructive documentation of the sample, whether it be an integrated circuit, package, an MLCC, even a printed circuit board. We want to look at the exterior and optically document that in a non-destructive manner before we go ahead and do any sample preparation, cross-section sample preparation to that, excuse me. We also can use real-time X-ray to document the sample in a non-destructive method. In this particular case, I'm using real-time X-ray to first find out where exactly the integrated circuit is located within this package. There may be one or more of these integrated circuits within this package as well. I want to understand that. In this particular case, there's just one. It's near the center of the package. We can see the corresponding wire bonds going from the integrated circuit out to the leads here, which were attached to the printed circuit board module. Here we can also observe if there were any defects with the wire bonds or going from the device to the external world here to the board. Just a higher magnification view of the integrated circuit showing those associated ball bonds to the circuit itself in the plan view orientation. We also need to understand, again, whether or not there's one or more of these devices present and what their orientation is in the Z-axis. So here's a side view image, X-ray image of that same integrated circuit to show that, in fact, this particular integrated circuit here is facing up, and so we want to come in from this top direction. It may be the case where this was on the, facing down, so we need to come in from the bottom of the package to expose the circuitry on the integrated circuit here within the package. So again, it's important that we understand the orientation of that device. So I went ahead and actually performed a wet chemical de-encapsulation processing of this device, and this is what it looks like after that's done. We can certainly see that the integrated circuit is exposed here. This is a optical image of that. Here's a higher magnification optical image of that integrated circuit. Again, another higher magnification view of that integrated circuit after the encapsulation. Even higher magnification optical image of a portion of the integrated circuit, along with a correlative SEM image. So here we can see, in the optical image, we can see the circuitry, we can see down through the passivation, we can see the underlying circuitry, etc. The ball bonds here are somewhat obscured in the optical image, where in the correlative SEM backscattered electron image here, we can easily see that these ball bonds are present and what they look like. However, the SEM only shows a surface view of the passivation in the integrated circuit here. But important, the correlative microscopy is quite important here. In this particular case, there's no defect present, but what I wanted to discuss was proper de-encapsulation methodologies here. So we're able to remove the component encapsulant material to expose the integrated circuit itself, to then examine it for potential anomalies or defects. And again, correlative optical microscopy and SEM imaging, we can see that it yields different information about the sample itself. And lastly, here we have a high magnification correlative optical and SEM images of a smaller area or high magnification area of the circuitry. We can see this is a quite a sophisticated device. And again, optically, we can see the integrated circuitry and the many levels or layers of circuitry that are present here. And then the correlative backscattered electron image, we can see that this is the passivation layer. We can see some demarcations here which are associated with these various signal traces in this particular view. And again, the correlative optical and SEM images show, different contrast mediums between or of the same sample. We can see color and we can see, circuitry below the passivation here, where in the SEM image we can just see the passivation layer. If there were a defect here, it might show up as this kind of dark region right here if it were an ESD or electrostatic discharge defect. And over here in the backscattered electron image, we can see that in this particular case, it's some residual encapsulated material that's left behind. But if it were an anomaly, such as an ESD anomaly, it would often look like a lightning strike happen here, and we'd see a hole and maybe some melted material, etc. And I think, so in review, we want to make sure that we get a good sample history and understand, what happened to the sample prior to the failure. We want to make sure that we understand what the failure symptoms are, and we want to make sure we have that information. We want to perform proper sample preparation techniques. That includes the removal of the coupons, the cross-sectioning, as we saw, and use of etchants that are correct and not too strong or beyond their shelf life. And very critical, we want to make sure that we analyze a control sample alongside of the failed sample. We want to make sure that that control sample sees the same exact analysis, sample preparation techniques, and analytical techniques that the failed sample does, so we can understand if the defects or anomalies we're seeing in the failed sample are in fact intrinsic to that device. A couple of notices. In this webinar, we did not use any client data or materials that were not used without permission. So any of the devices we looked at, we had permission from our clients to look at. If you are interested in a custom webinar or consulting, we can certainly provide a private webinar or seminar directed specifically to your industry or company, working with your types of materials and samples. So please contact us. Also, as I've done in the past, I certainly could travel to your facility to observe your personnel performing cross-section sample preparation and recommend any tweaks to their processing that may help generate better cross-sections. Please check our website for the upcoming webinars. I know Christina had spoke a little bit earlier about the next one that's going to be coming up. It's going to be a actual real live analysis from a sample that we choose that's been submitted. So please check on that. And lastly, if you have any questions, you certainly can type those in now. You can also send questions after the fact to our email address, answers@analyticalanswersinc.com. And please visit our website, analyticalanswersinc.com. And thank you for your valuable time today on St. Patrick's Day. Thanks.